During this section, we'll solve a system of linear equations by graphing. So let's first talk about what we mean by a system of linear equations. A system of linear equations consists of two or more linear equations. We will concentrate on systems consisting of two linear equations in two unknowns, such as this. Now let's talk about what we mean by a solution of a system of linear equations. A solution consists of an ordered pair of numbers that satisfies both equations in the system. So we'd like to know, is this ordered pair of numbers a solution of this system? To see if it is, we need to see if it is a solution of the first equation and also a solution of the second equation. So let's do that. Let's start with the first equation. I'm going to let x be 3 and y be 4. If x is 3 and y is 4, is this a true or false statement? Well, 3 times 3 is 9. 9 minus 4 is 5. 5 does equal 5, so this is a solution of the first equation in the system. Now, is it also a solution of the second equation in the system? Well, let's see. Let's now check the second equation. If x is 3 and y is 4, is this true or false? Well, that's 3 plus 2 times 4 is 8. 3 plus 8 is 11. 11 does equal 11. So is this a solution of the system? The answer is yes, because it's a solution of this equation and also a solution of this equation. Let's check another ordered pair. Let's look at, say, negative 5. And let's see if that is a solution of the system. Let's start with, makes no difference. Let's go ahead and start with the second equation since I have my arrow drawn here. All right, I'll start with the second equation. If x is 0 and y is negative 5, does that equal 11? Well, let's see. 0 plus 2 times negative 5, that's negative 10. Is negative 10 equal to 11? The answer is no. That is a false statement, which means this is not a solution of the second equation. It doesn't even matter if it's a solution of the first equation. I do not even need to check. Since it's not a solution of the second equation, the answer is no. That is not a solution of the system. Thus far, we know a solution to a system of two linear equations in two variables is an ordered pair solution in common to these two equations. Since it is a solution in common, doesn't it make sense that if we graph this linear equation in two variables and graph this one, that the solution is a point in common? And that happens to be the case. That's how we will solve systems of linear equations in two variables, by graphing. We will look for points of intersection. So let's do that. Let's solve this system of linear equations in two variables by graphing. I'll begin by graphing this first equation, so concentrate on the first equation only. And here I've set up a little XY grid so that we can organize our ordered pair solutions. To graph this, we'll come up with 3 ordered pair solutions, and then we'll graph the 3 points and draw a line through those 3 points. So let's suppose x is 0, and then maybe we'll let x be 2, and then negative 2. If x is 0, we have 2 times 0 plus y is equal to 0. 2 times 0 is 0, so we have y is 0. This is an ordered pair solution of the first equation in our system. What if x is, say, 2? Well, if x is 2, I'll have 2 times 2 plus y is 0, or 4 plus y is 0, or y is negative 4. So when x is 2, y is negative 4, and now let's let x be negative 2. If x is negative 2, we'll have 2 times negative 2 plus y is 0. That's negative 4 plus y is 0, or y is positive 4. Now let's plot these 3 ordered pair solutions of the first equation, and let's draw a line through them. 0, 0, 2, negative 4, that's 2 to the right, 4 down. And then negative 2, 4, that's 2 to the left, and 4 up. And now let's draw a line through those 3 points, and that is the graph of the first equation in our system. Every single point on this line is represented by an ordered pair, and it is the solution of the first equation. Now let's graph the second equation, so let's write up another table. Oh, let's suppose x is 0. Maybe we'll go with 1 and negative 1 this time. So, concentrating on the second equation, let's let x be 0. So we have 3 times 0 plus y is 1. 3 times 0 is 0, so y is 1. What if x is 1? Let's see what happens. If x is 1, we have 3 times 1 plus y is 1. 3 times 1 is 3, so we have 3 plus y equals 1, or y is 1 minus 3, or negative 2. So when x is 1, y is negative 2, and now let's let x be negative 1. All right, so we'll have 3 times, if x is negative 1, plus y is 1. 3 times negative 1 is negative 3. And then y is 1 plus 3, or 4. There we go. Let's plot these 3 ordered pair solutions of the second equation, and let's graph that second line. So let's see what we have. I have 0, 1, that's 0 left or right, and 1 up. And then I have 1, negative 2, that's 1 to the right and 2 down. And then negative 1, 4, that is 1 to the left and 1, 2, 3, 4 up. So there are mine. Now make sure you don't get the points mixed up. This point, and that point. Those are my 3 points here. Let's draw a line through the 3 points. So here's my straight edge. And now I'll draw a line representing the graph of the second equation in this system. And there we have it. Now we're looking for any points in common. Do these 2 lines intersect? The answer is yes, and they appear to intersect right at this point with coordinates 1, negative 2. So it appears that this system has one solution. Now how can you check? We're just guessing at this point. We can check by letting x be 1 and y be negative 2 in the first equation, seeing that a true statement results. Do the same thing in the second equation, see that a true statement results. If so, we are correct, and we have solved this system by graphing. By the way, if equations have different graphs, we call these independent equations. And if a system has at least one solution, we call it a consistent system. So this is a consistent system, and we happen to have independent equations. Let's now look at another system of linear equations in 2 variables. Let's suppose we have the system, x plus y equals 5, and then x plus y equals 6. This is a linear system of equations in two variables. We'll graph each of these equations. So I'll set up a table. Let's concentrate on, say, the first equation in the system, and let's see if we just can't mentally write down some solutions. The x and y value should have a sum of 5, and then we do have ordered pair solutions. So suppose x is 0, y must be 5, or if x is 2, y must be 3, or if x is 1, y must be 4. There are 3 ordered pair solutions. Let's graph them. 0, 5, that's 0 left or right, 5 up. 2, 3, that's 2 to the right, 3 up. And then 1, 4, that's 1 to the right, 1, 2, 3, 4 up. And there's our 3 points. They all lie on the same straight line. And now let's graph. I'll draw the straight line through these 3 ordered pair solutions. So this is the graph of our first line. Now let's graph our second line. Same thing, we'll set up a table. X, Y, and we're looking for 2 numbers whose sum is 6, so let's go ahead and just mentally do this. If x is 0, y is 6. Actually, if y is 0, x is 6, and you can use 3 and 3 if you'd like. 3 ordered pair solutions. Let's now graph them. 0, 6, that's 0 left or right, 6 up. 6, 0, that is 6 to the right, 0 up or down, and then 3, 3, that's 3 to the right, 1, 2, 3, up. There we go. All right, do you see these 3 points? Let's graph them. Now, it appears that our 2 lines in this case are what? It appears that they are parallel. Now, of course, graphing is not a very accurate way of solving a system. We can't just look at them and say, well, they appear to be parallel, and by the way, since they do appear to be parallel, the system then has no solution. No, instead we need to look at these 2 equations. Let's take the first one, x plus y equals 5. Let's actually check the slope of each equation, because if the slopes are the same and there are different y-intercepts, then we do have indeed parallel lines. To find the slope, solve for y. Let's do the other equation, x plus y equals 6. Solve for y, that would be negative x, negative 1x or negative x, plus 6. Now, what is the slope of this line? It is negative 1. What is the slope of this line? It is the coefficient of x, which is negative 1, and we have different y-intercepts, so these are indeed parallel lines, and they are then, or shall we say the system has no solution. Now, by the way, since the system has no solution, this is an inconsistent system, but the equations still are independent because the graphs are different. Let's try another system of equations. We are solving systems of equations by graphing. Let's suppose I have the system, let's say 6x minus y is equal to 4, and 1/2 y equals negative 2x. No, let's make that negative 2 plus 3x. Negative 2 plus 3x. All right, here's my system of equations. I'd like to solve this system of equations by graphing. So let's graph each on a rectangular coordinate system. So here is my table, and I will look at the first equation only at the moment. All right, let's let x be, well, it's always nice to let x be, say, 0. If x is 0, Then I have negative y is equal to 4. I'll let you solve. Divide both sides by the coefficient of y, which is negative 1, and y is negative 4. Negative 4. There we go. What if y is 0? Well, if y is 0, then I'm solving 6x equals 4. Let's go ahead and write that down. Divide both sides by the coefficient of x, which is 6, and x is 4 over 6, or 2/3 simplified. There we go. Let's try another one. What if y is, say, negative 2? Well, let's see what happens. If y is negative 2, then we have 6x minus y is negative 2 is 4. So we have 6x plus 2 is 4. We have 6x is 4 minus 2, or 2. And then x is 2 over 6, or just happens to be another fraction, 1/3. All right, so 1/3. Now let's see if we can't graph this correctly with these fractions. All right, 0, negative 4, 0 left or right, 4 down. 2/3 0, where is that point? I start at 0, I go 2/3 of a unit, and then 0 up or down. So be very, very careful. There is that point. And then where is 1/3 negative 2? We start at the origin, we go 1/3 to the right and 2 down. 1/3 to the right and 2 down. There it is, and you can see that these 3 points do all lie on the same line. So let's draw the line through them, and that is the graph of what? That is the graph of 6x minus y is equal to 4. Now let's graph our other equation. To do so, it's really up to you. If you do not like to work with fractions, that 1/2 y equals negative 2 plus 3x, you can multiply through by 2. And if I multiply through by 2, 1/2 times 2 is 1y, or simply y. Negative 2 times 2 is negative 4, plus 3x times 2 is 6x. So this is equivalently the same graph, or the same equation as that second one of the system. All right, let's come up with some ordered pair solutions of that system. By the way, if I write this as y is equal to 6x minus 4, we know the slope is 6, and we know the y-intercept is negative 4. So I know if x is 0, I get negative 4. What if x is 1? If x is 1, what is 6 minus 4? That's 2. And what if x is, I don't know. Let's see. If x is 2, I think we'll be off of our graphing here. If x is 2, that's 12 minus 4, or 8. And we can certainly graph it, but my system goes up to 6 right now, and I don't want to extend it. What if x is a half? What do we get? If x is a half, what is a half of 6? A half of 6 is 3, and what is 3 minus 4? It's negative 1. So there we go. You can double check me on those ordered pair solutions. Let's now graph though. 0, negative 4 right here, 1, 2, well right there, and 1/2, not 2/3, but 1/2, negative 1 right there. Can you see that these 3 ordered pair solutions lie on the exact same line? So these graphs are exactly the same. What does that mean in terms of number of solutions of the system? How many points are there in common? There's an infinite number of points in common. So there's an infinite number of solutions. Now you can check by writing each of these in slope-intercept form. If you do so, same slope, same y-intercept, and so you'll know that the graphs are exactly the same. But this is an infinite number of solutions. We call these equations dependent equations, and we also still call this a consistent system because we do have at least one solution. So let's review what we talked about while graphing. Here we have two lines with one point of intersection, so the system has one solution. We call it a consistent system, and these are independent equations. Another case is where we have parallel lines, then the system has no solution. We call this an inconsistent system, and the equations are independent equations. Finally, what if we have the same line when we graph the equations in our system? Then there is an infinite number of solutions to the system. We call this a consistent system and dependent equations. I hope you can see by now that graphing is not an accurate way for solving a system of equations. We don't need to graph a system, though, if we're just interested in knowing how many solutions a system has. For example, how many solutions does this system have? To determine this, we simply need to write each equation in the slope-intercept form. Now, how do you write an equation in the slope-intercept form? You solve that equation for y. So if I write this equation in the slope-intercept form by solving it for y, I'll subtract 4x from both sides. So y is negative 4x plus 24. Solve this equation for y. I'll let you do so, but you'll have negative 1/2 x plus 1. And now you just concentrate on the slopes and the intercepts. Since these slopes are different, then the lines will intersect, and when the lines intersect in one point, then the system has one solution. So these represent intersecting lines because the slopes are different. That means that these lines will intersect in one point, so there is one solution to this system. Let's try that again. Let's look at another case. Let's suppose we have x plus y equals 4 and x plus y equals 3. We just want to know how many solutions. So I'll solve this equation for y. Y is negative x plus 4. I'll solve this for y. Y is negative x plus 3. Now concentrate on these equivalent equations, equivalent to the original ones in the system. The slope of this graph is the coefficient of x, negative 1. This slope has this graph has a slope of negative 1. Since the slopes are the same and the y-intercepts are different, these are parallel lines. Now, parallel lines do not intersect, which means the system has no solution. Same slope, different y-intercepts, no solution. And let's try this one more time. Let's suppose I have the system 6y plus 4x is equal to 6, and 3y minus 3 is equal to negative 2x. If you write this in slope-intercept form, you'll have y is equal to negative 2/3 x plus 1. If you write this in slope-intercept form, what happens is you have exactly the same thing. Since you have exactly the same thing, same slopes, same y-intercepts, what will the graphs look like? Identical lines, same exact line. So as far as solutions of the system, how many solutions do we have? We have an infinite number of solutions. There we go, just using the slope-intercept form. At this time, practice solving systems of linear equations by graphing. Let's now check your knowledge of systems of equations by answering the following question. Which system has exactly one solution? Is it choice A, which consists of the system y equals 3x plus 2 and y equals negative 3x plus 2? Is it choice B, which consists of the system of y equals x minus 2 and y equals x plus 3? Or is it choice C, which has the system y equals 4x minus 2 and y equals 4x minus 3? The video will pause, then make your selection. Choice A is the correct choice. Let's talk about why. The coefficient of x, which is the slope, here is 3. The coefficient of x, which is the slope here, is negative 3. As long as the slopes are different, the lines will tilt differently and will eventually intersect in one point, which then means one solution. So choice A is the correct choice. Choice B is incorrect. Let's talk about why. The coefficient of x is the slope, it is 1. The coefficient of x here is the slope, it is 1. So we have two lines that tilt the same way. It's either going to be same line or parallel lines. Because the y-intercepts are different, we do have parallel lines. Parallel lines in a system means no solution to the system. So this is incorrect. The correct choice is choice A. Remember, the system there is y equals 3x plus 2 and y equals negative 3x plus 2. Here we had different slopes, which means the lines tilt differently and they will eventually then intersect in one point. Choice A is the correct choice. Choice C is incorrect. Let's talk about why. The coefficient of x here is the slope of this line. It is 4. The coefficient of x here is the slope of this line. It is 4. We have two lines then with the same slope, which means they'll be the same line or parallel lines. Because we have different y-intercepts, these are parallel lines, and remember then, since they don't intersect, the corresponding system has no solution. The correct choice is choice A. It consists of y is equal to 3x plus 2 and y equals negative 3x plus 2. Notice these slopes are different. Because the slopes are different, the two lines tilt differently and they will eventually intersect. They'll intersect in one point, which will be the one solution to the system. Choice A is the correct choice.